Well, welcome back, everybody. I hope everybody had a good weekend. All right, couple. I sent an email to remind you, friendly reminder that exam number 2 today will close at 10 p.m. So give yourself plenty of time. Keep it simple. Now, this one's going to take. Is probably going to have a lot more questions as far as you write something concerning a friend or something, and I've been reading a lot of the one of the activities. And here's some suggestions. In fact, this is a suggestion that my advisor gave me back 100 years ago. He told me that, 99% of you, 99.99% of you are going to be in some professional field. You're going to be writing things for some report or writing things for somebody to read at a later date. And so it's quite crucial, especially in science, but in general, it doesn't have to be science, that when you write something, that you write it specific with the information. And what does that mean? Well, it's this. When you write something, write it in a manner that if you read it again 10 years from now, you know exactly what you were trying to state. Okay. And there's no question whatsoever. Sometimes I know we get in a rush. We want to write a sentence and we want to write something. I'm trying to follow what you've written and I understand what you're saying, but the sentence doesn't make sense. Okay. But so take a minute when you write something, go back and read it. Does it make sense? And I read this thing 5, 10 years from now and understand what I wrote. More importantly, can someone else read it? You could be leaving important notes. Most half of my class here is nursing students. You're going to be writing reports. It's very important that you write exact, distinct notes for the next nurse coming in on shift with information concerning your patient. Engineers, same thing. You're going to be passing information on to other engineers. That's what I mean. This ability to write something is very, very crucial, very important. So when you write something, uh, write it such that it makes sense. Okay, have someone else read it if you can. Okay, doesn't mean to help you write it, but they can read it for you and see does it make sense to them. Okay, all right. Enough said on that. Any questions? Today the exam is chapters 4 through 6. There's a lot of questions that I need to answer, so it's going to take me a few days to grade everybody. So bear with me when you get done. I'm probably getting done all completely. All right. Uh,
Um,
Somebody had a question. They unmuted yourself. Who was that? No. Yes. No.
I did, yes, actually.
Yeah. Go ahead.
It was just atomic size. For some reason, I'm still struggling
Okay. Good question, because that was my next note here. I was gonna the
a little
last
bit on it.
yeah the
Mostly
activity
fine.
the activity. There was one activity where you did a comparison between two atoms and trying to determine, one atomic size, which one's bigger. Okay. And then the other aspect was the other question was who has the highest ionization energy. Now they're interrelated here. Think about this for a moment. Let me pull up the periodic table real quick. There it is, right there. Let me make sure I pull the periodic table. Okay. So here's our periodic table. Now, as you go down the periodic table, someone had a question. Oh, as you go down, let me get my arrow here. As we go down the periodic table, okay, remember we talked about the energy levels that we have. There's 7 energy levels where the electrons fill up. So you start with the first energy level, fill that level with electrons, and move on to the second, third, and fourth. So obviously, as we go down from element 1 through 818, we're picking up 2 things greater in number. That is protons and electrons. Okay, and the protons, remember, define what the element is. Second of all, the protons have a positive charge. Okay, the electrons, as you know, have a negative charge. There is a force between them that want to attract each other simply because we got a positive and a negative. Okay, so as we increase the number of protons and electrons, we put the electrons in specific orbitals, specific energy levels. So as we go down the periodic table, we go from period 1, which is the first energy level, down to period 7, which is the seventh energy level. Okay. And so you can see, hopefully, that as we go increasing the energy levels, the atom gets bigger because that is occupying the outermost layer for the electrons. So if we compare lithium number 3, which has 3 protons and 3 electrons, and we compare that with, let's say, cesium number 55, notice that, let me highlight them so we know where we're talking about the same one here. We know which one I'm talking about. If I compare lithium or cesium, and for that matter, I could pick any one, Ti with Zr, okay, or manganese with this guy here. As I'm within, I can compare nitrogen with element number 115, okay? Anyone, as long as I'm going down the periodic table, the element gets bigger because the valence shell is occupying the outermost energy level, which is number 7 if I'm down here in level 7, okay? So the radius for atoms as we go down the periodic table increases. Now, I hopefully that's that makes sense, okay, with respect to going down the periodic table. Now, where the challenging part is, and it is going across the periodic table. So let's just go across the periodic table right here. We're going to go with energy level number 4, but we can do that for any of them, 1 through 7. But we're going to just arbitrarily pick number 4. So I'm going to compare potassium number 19. Okay, let me highlight that, number 19, with krypton way over on the other side. Okay, krypton number 36. And the question is, all right, well, here, which one is larger, for example, in size, or which one has a higher ionization energy? Okay, so we can answer those 2 questions because they're interrelated. Now, the first thing to notice that we're in the same energy level. So we're not going down to another energy level. We're all in the same level. Okay, so with respect to energy level, we're in energy level number 4. There's a slight difference in diameter, even though we're in the same energy level, and that is attributed to the number of protons and electrons the element has. Potassium is number 19. As we know, it has 19 protons and 19 electrons. All the way to the far right, we have krypton. It has 36 protons and 36 electrons. And as we go across the periodic table, that's what's increasing. We're increasing the number of protons by 1 from 19 to 20, 20 to 21. We're increasing the number of protons by 1 and correspondingly increasing the same number of electrons. So we're increasing the protons as we go from left to right. Now, as we get to the far right and we compare the difference, potassium almost has about half less protons than krypton. There's a lot of nuclear force, if you want to call it nuclear magnetic force, that That would be true because it's almost true, but better you just call it nuclear force. Why? Because it's got a positive proton attracting the negative charge electron. And the more positives we have corresponding with the more negatives, that force increases, gets stronger. The result is the radius of krypton, okay, is much smaller than the radius of potassium because there's a lot more nuclear force, if you will, that's attracting, that is occurring because of the force between the proton and the electrons, yanking it in, okay, which is related to the ionization energy. Because as that force increases, those electrons are not going to be given up very readily. They're being held a lot tighter as we go across the periodic table. And so the ionization energy for krypton will be much greater than potassium, much, much greater. Okay. And that would be true for the elements as we go across. So if we were to compare number potassium with calcium, okay, 19 to 20, well, 2 points. As we go to the periodic table, because calcium has one more proton, one more electron than potassium, that force, nuclear force increases, so its radius is smaller. And second of all, its ionization will be greater because potassium holds on to those electrons with a lot more force than potassium, okay? And we can go across, all the way across the periodic table, maybe go all the way to selenium number 34, same reasoning. Now, yes, as we go across the periodic table, we could also say that as it becomes more non-metal in nature, because the nature of the non-metals is to gain electrons and not leave it, not get rid of it, that the ionization energy is higher. They go hand in hand. The fact that becoming more non-metal means there's more protons, more electrons holding on to those electrons much, much stronger than the metals. Okay. So that in a nutshell, I think, explains why the radius changes. Down the product table, we simply get a bigger onion, layer of the onion. We're going different 7 energy levels, okay? And that's why down the product table, it's bigger. Now, one other aspect. We talked about valence electrons. So, and I stated, if you look at the Roman numeral A, the A elements, that number corresponds to the number of valence electrons. That is not true for the B, okay? So B, for manganese number 25, we can't say there's 7 valence electrons because it's in Roman numeral 7B, okay? It's a little bit different, so we can't compare that. Only for the A, we're 100% sure of the number of valence electrons. Okay. All right. Hopefully that explains it a little bit better. What do you think? Any other questions about that with respect to the radius? And what the trend is? Now, again, you might be asked a question about a specific trend, and that's the thing. Yes, you can state the trend, but explain why the trend happens. Yes, we know, based on what I've told you, the trend is down the periodic table, but the radius gets bigger, and it gets bigger because we're just getting a bigger element. Okay, across the periodic table, radius gets smaller. That's a trend. And that is because we're picking up more positive and more electrons, and that force between the two, the attraction gets greater, causing the radius to get smaller as we go across the periodic table. Okay, which is in line with ionization energy. As we go across the periodic table, the general trend is the ionization goes up, and it's simply because the electrons want to hold on to, those elements want to hold on to their electrons much greater than the metals. Okay. Any other questions? Hopefully that answered that for you. All right. If not, I will continue with the chapter we have finished on slide number 13 on chapter 7. Okay. And this is 13, but I want to back it up for a second. And I just want to remind you about covalent bonds. There's two types of bonds. We have an ionic bond, which is a combination of a metal and a non-metal. That's important. Ionic bonds are a combination of metal and non-metal. Covalent bonds are a combination of non-metals, two or more non-metals. Now, in ionic bonds, it's more of an electrostatic attraction as analogous to two magnets attracting each other. Ionic compounds, when placed in water to dissociate, totally dissociate. Some dissociate 100%, some dissociate maybe much less, 5–10%, but they do dissociate into the full-fledged positive charge and a full-fledged negative charge. Covalent bonds do not do that, okay? Covalent bonds are literally sharing electrons. And so instead of having electrostatic attraction, there is an absolute sharing of electrons between two atoms that are non-metals. There could be equal sharing and unequal sharing, much more on that down the road here, okay? Now there's three types of bonds. There's a single bond, which encompasses two electrons that are being shared, a double bond, which is 4 electrons, and a triple bond, which is a total of 6 electrons, okay? Now you will see it a lot with respect to when we write it, you'll see lines. And so let me see if I can do it. If I do carbon, yeah, it's a bad example. A single line that represents a single bond. 2 lines represent a double bond, and this is between carbon and carbon. And 3 lines represent a triple bond. Every line there, every line right here is 2 electrons, okay? All right, go back to that. Now, it was thought, since we've been talking about radius, that it was believed that when 2 non-metals came together to form a bond, it was believed that the bond length that they formed would simply be the sum of each individual radius of each element, okay? And so, for example, hold on. If we take the hydrogen atom, it has a radius of approximately 0.037 nm, which represents nanometers, 10⁻⁹, very small, okay? Nano. You've all heard of nanobots. Okay, we're down to the atomic scale when we talk about nano scale. The hydrogen atom has a 0.037 nanometers, with the chlorine atom having a 0.099 nanometers with respect to the radius. It was believed that when they come together to form this molecule called HCl, hydrochloric acid, that the bond length between the two will be simply the sum of each individual radius, and that would be 0.136, the radius of a hydrogen, the radius of the chlorine. It was determined that that's not the case. In fact, the bond length is much less. It's 0.127 nanometers. And it is believed the reason it's less is because what's happened, the one electron coming from that electron that's being shared between the hydrogen and the chloride, those 2 electrons right there, when have the arrow actually overlap, okay? And so they're not just next to each other, but there's a little bit of overlap because of the sharing. Now, this example here is a covalent bond, but it is an unequal sharing. And the reason it's an unequal sharing is because chlorine has a higher electronegativity. Remember that property, En? Electronegativity is the affinity to attract electrons in a bonded situation. And so here we got chlorine bonded with hydrogen, Okay. Chlorine has a higher electronegativity, so it tends to pull the electron density in that bond more onto itself. So we have an unequal sharing that we're going to talk about as we down the road, and we call this a polar bond, unequal sharing. All right. So what do we, when we talk about bond breaking and bond formation, we have to introduce energy. Okay. So energy is required whether we break or form a bond, conservation of energy. So, for example, when we break a bond, it always requires energy to break a bond. Okay? And so what's happening here is energy is what we call a reactant. What do we mean by reactant? That is, it is required, and I'll have an arrow here in a moment, but because it's a reactant, it needs energy, and what happens, it takes energy from the environment. And this type of process is called endothermic. And if we were to measure the temperature, guess what? It will get cold. You might be familiar with this if you go to the pharmacy by yourself, go to CVS or whichever pharmacy you go to and get a cold pack. All right. You got a plastic a bag with chemicals in there. And what you do, you're asked to break that pack, break it up. There's a chemical inside that's broken up. Process occurs, it gets cold. Okay. It's an endothermic reaction because in that process requires energy and it takes the energy from the environment, which results in a cold container. Yeah. So we can put that cold material on your shoulder or wherever you need a cold pack. Now, this is what we mean by being a reactant. When we write a process, a chemical or physical process, we have that infamous arrow, okay? To the left of the arrow are the reactants. To the right of the arrow are the products. So in this case, energy in the form of heat is on the left of the arrow and it is a reactant. Now, when we form a bond, okay, so breaking a bond up requires energy and it's endothermic. When we form a bond, there is energy release. And energy release, we call that an exothermic process. Also, you can get a hot pack at the pharmacy. You smack it, it gets warm. Okay, the chemicals involved in there, there's bond forming resulting here. There's energy being given off. You can put that hot pack on your arm or whatever you're injured injury on your body. Okay. In this case, energy is a product. It is produced. So we put it on the right side of the reaction arrow. It is a product. Okay. And giving off is heat. All right. So with that being said, a couple of questions. Here we have a true and false situation concerning this chemical, H2S. Okay. Dihydrogen sulfide, very nasty smelling material. All right, so they're asking you the question, electrons are shared in H2S. Well, to answer that, we have to remember the two types of chemical bonds we have. Covalent bonds are being shared, ionic bonds are not being shared. Okay, so we know that. Now, how do we distinguish between an ionic bond and a covalent bond? Ionic bond, it's a combination of a metal and a nonmetal. Covalent bond is a combination of two or more nonmetals. We have H2S, hydrogen, nonmetal, sulfur, nonmetal. Therefore, we have a covalent bond here, okay? Covalent bond. We relearn that just simply by looking at the atoms of the structure of the compound we're given here. Okay, H2S. So the answer here is true, simply because we just determined that it is a covalent molecule here, and therefore the electrons are being shared. Nothing about unequal sharing or equal sharing, but you'll see that it is definitely unequal sharing because the sulfur is the central atom and the hydrogen are the two atoms that are bonded to each other, to the central atom. And the electronegativity of hydrogen is much less than the electronegativity of sulfur. Therefore, we have unequal sharing going on. All right. The bond between H and S is ionic, and that would be strictly a false statement because we needed to determine what type of bond it was in question number 1. So this is totally false because we don't have any metals involved. Okay? Now, if this were this compound, which is a real compound, is Na subscript 2S, okay? If we replace the hydrogens with sodium, 2 of them, then we have sodium sulfide. Now we're talking about ionic compounds. And question number 1 would be false if it was sodium sulfide. Question number 2 would be true if it was sodium sulfide. Okay. The HS bond length is less than the sum of the 2 atomic radii. That is true. Okay, remember we had that slide where we had the molecule H hydrochloric acid, HCl. It was thought that the radius of the hydrogen and the chloride, the total bond length would be the sum of those 2 radii, and that's not the case. It's much smaller, okay? Much smaller because there's overlap in this covalent bond. And then breaking HS bond releases energy, okay? And that is false. Breaking the bond requires energy and becomes endothermic, okay? Oop, turn that up. Now, which brings us to this thing called Lewis dot structures. Now, if you've not done this yet, I would do it as soon as you can because we will be using the shapes table, okay? In the shapes table, we have 4 columns here. The first column is a general formula. I repeat, general formula. It's not an actual formula. A represents, you see, when we give you a formula, we're going to tell you who is the central atom. And so we have the central atom, and then everybody is bonded around the central atom. A here in the first column, let me highlight that here. These are the general formulas. A represents the central atom, which you'll be told who is the central atom. B represents the atoms that are bonded to the central atom. They could be the same or they could be different, okay? And then E represents what we call lone pairs on the central atom. We would have, for some structures, 2 electrons that are on the lone pair. And that's denoted by down here where we have double arrows. So let's take the very bottom one here. Okay. Now we got the central atom, and then we got 2 spheres that are bonded to the central atom. But also we have what are called lone pair electrons that are on the central atom. And the letter E represents those lone pairs. Sometimes we have lone pairs, sometimes we do not. For example, in this general formula, guess what? There are no lone pairs on the central atom. There are just 4 atoms bonded to the central atom, okay? And then what happens is that as we start putting lone pairs in there, they start to change what we call the bond angle. So if you go back up to the AB4 example, that is the most common configuration we find of compounds out in nature. It's called tetrahedral, okay? And normally it's the central atom with 4 things bonded around it. Remember that every line represents 2 electrons. We got 4 single bonds around it. They're electrons. They got a negative charge. They're being shared between two different atoms here. Okay. And because they're electrons, every bond is going to repel each other because they're negative charge. So this configuration is the optimum configuration that they have that causes all the electrons to repel. You end up with this particular shape called tetrahedral, and there's an actual bond angle between the moieties that are bonded to the central atom, and that is 109.5. That particular bond angle is very unique and is found quite a bit out in nature. Now, what tends to happen is if we take out one of those spheres and start adding just the central atom onto the molecule, like here, where we have one pair of central atoms. Remember, they're not bonded. They're just two dots. Those two dots represent two electrons. That shape that you see that looks like a oval shape, that's just to demonstrate an orbit, okay? It's not part of the structure. It just kind of demonstrates what the orbit is. And because those two electrons are negative charge, they repel each other. The result is that that bond angle between whatever is bonded to the central atom gets shrunk, and it becomes less than 120 degrees compared to, let's say, this one up here, where we have uh, three moieties bonded to the central atom, and they're all equally spaced around the central atom. We have a bond angle of 120 degrees. Okay, we call that trigonal planar. It has a specific name for that shape. But the moment we start adding lone pairs into the central atom, that bond angle between the moieties that are bonded to the central atom, they get distorted. Okay, let me erase some of this. It's getting kind of messy here. And as we add more um, lone pairs, that angle gets bent even much less, 109.5, less than 109.5. So the point is this: one, we're going to give you a formula. From there, we're going to determine the structure based on the valence electrons. So you refresh your memory about the number of valence electrons for the A elements, okay? And from that information, we're gonna come up with a general formula. The general formula for that compound will give us the geometry, which is the second column, which would then give us the name, the shape of that geometry, which would be linear, trigonal planar, etc., tetrahedral, and plus gives us the bond angle. Okay, so all we need to figure out is the general formula. And from that, the rest we use the table to tell us the geometry, the shape, and the bond angle. Okay. And this is what we're going to use Lewis dot structures. But first, let's do the Lewis dot structures of the specific atoms themselves. Very straightforward. All we got to figure out is the group number that they're in. That tells us how many dots we need, and we're done. Now we simply put dots around the atom for the number of valence electrons it has. We pretend that the atom is a square, and we start put one drop on one side of the square and then go around the atom. Whether we go clockwise or counterclockwise makes no difference. Just fill up the 4 sides before you refill a second side. Okay, so for example, we got potassium, oxygen, silicon, magnesium, and iodine. All we need to do is find them on the periodic table, determine what group it belongs to, and guess what? There you go. We got potassium, which has 1 valence electron, it's in group 1. Okay. We got oxygen, which is in group 6, has 6 valence electrons. We got silicon, which is in group 4, 4 valence electrons. We notice we put the 4 all the way around the element, don't group them together. We start filling them up just like we did the orbitals. We fill up one, move on to the next one until they're all full, and then we just keep doubling up as we go around. The ultimate goal is to have 8 electrons. So we had a noble gas here. It would be, it could be anyone, argon with the symbol AR, and then 8 dots all the way around. And magnesium's in group 2, so 2 dots. And iodine, group 7, is part of the halogens. Okay, so 7 dots. So that represents the Lewis dot structures for the specific atoms, and specifically only for the A atoms. That's group 1 through group 8A. Okay, now for structures. Okay, how do we do that? Well, the first thing we do is we add up the total number of valence electrons that every atom contributes to the structure. Remember something, you're going to be given the central atom. You'll be told who the central atom is, and then everybody's bonded, whatever's attached to it, everybody's bonded to the central atom. 9 times out of 10, the central atom is written first, not always, but if that's the case, you always be told, or it will be written in bold letters, or it will be underlined. Okay, so we tally up the number of valence electrons, and then we surround the central atom with all the other atoms and draw a single line. That single line represents a bond, and that takes care of X amount of valence electrons that we have to begin with. Now, that total number of valence electrons that we calculate, that is what you got to work with. You cannot just magically put in more valence electrons as needed. And the converse of that, you cannot just remove them because you ended up with too many. Normally, if you ended up with too many, it's a math problem that maybe you determine which group it was incorrectly, gave it the wrong group number. They give you extra electrons. And if you don't have enough electrons and you end up with you're short, then we start creating double bonds and single and triple bonds as needed. We'll go through some examples of that. Okay. Now, what I like to do is, because it keeps the numbering a lot simpler, is once I figure out the total number of valence electrons, you should, if you got the right number, will always have a number divisible by 2. Once I have that total number of valence electrons, I divide by 2, and that gives me pairs of electrons. So I can now just draw lines and keep track of pairs. You don't have to do that, but it helps me with keeping track of all my electrons. And as you go along making structures, to remember back in your head, 2 rules, the duet and the octet. The duet rule is for hydrogen, okay? Hydrogen will always only have a single bond around it, 2 electrons around it. It doesn't have the octet rule. Remember, hydrogen and helium have the duet rule. Everybody else has to have 8 electrons around it. Those electrons could be non-bonding, or they could be bonded with something else that they're shared with. Okay, if they're shared with another atom, that single bond is counted toward both those atoms that share it. Okay, it'll make more sense here, hopefully, as we do an example. So remember the octet, except for hydrogen. Okay, then once we've accounted for all the electrons, we double check to make sure that we have the same number we calculated in number 1. Okay, make sure that adds up, make sure that the octet is fulfilled. Then we determine the bonding electrons and the lone pairs. Okay, from that information, we're going to be able to determine the general formula, which sends us to the shape table, which then tells us the name of the geometry and the bond angles and so forth. If we reach a point where we put all the valence electrons there and we can't make the octet rule, that is where we start creating double and triple bonds, okay, to make sure the octet is fulfilled for everybody. All right, so let's take, for example, water. So here's a formula. I got water. Oxygen is the central atom. So we're going to underline that. That's the central atom. And so we have oxygen and 2 hydrogens bonded around the central atom. So the first thing we do is we add up all the valence electrons. What do we know about hydrogen? Each one has 1 valence electron. It's in group 1, and there's 2 of them. So it's 2 times 1. Okay. And then we look up the group number for oxygen is in group 6. So we have a total of 8 valence electrons to work with. 8, or 4 pair. Okay? Or 4 pair, because that is divisible by 2. If you come up with an odd number, then your mathematics is wrong, or you got the wrong group number. Okay, so you always should have a number divisible by 2. All right, we know that oxygen is a central atom. And so I can very quickly type in hydrogen bonded to oxygen, bonded to hydrogen. Okay, guess what? That took care of 2 pair, right? 1 pair for one hydrogen and oxygen, and the other pair for the other hydrogen oxygen. So that means I got 2 paired left from the original 4 pair, and I need to put them someplace. Well, I can't put those 2 pair on hydrogen. Why? Because hydrogen now is happy with this duet. There is a pair of electrons around hydrogen on both of them. So the only logical place that they can go is, oh, don't know if I can draw it. Ah, terrible line. That line represents a line on the oxygen. Okay, so that's the only place. Let me see if I can clear that up a little bit. Okay, and so I had oxygen. I had oxygen. There we go. Try this again. My little writing pen is not cooperating. Okay, so that's what I had right there. And now the other 2 pair, the only place I can put them is on oxygen itself. Right? Now count my lines. I have 4 lines that represent 2 electrons. Okay, which means I have 8 valence electrons, which is what I started off with. 8 valence electrons. Okay. And that is my formula. The hydrogen's happy because its duet rule is fulfilled. The oxygen is also happy because its octet is fulfilled. And there's 8 electrons around it. 4 of them are being shared with the hydrogen, and the other 4 are on the oxygen itself, which means I have a lone pair, an E. So the general formula I have here for water is A, okay, which represents the oxygen, B, which represents whatever's bonded to the central atom, subscript E2, and I can do subscript on my thing here, so that 2 is a subscript. There's 2 B's, in this case 2 hydrogens, and E subscript 2, okay? That is the lone pair on the oxygen. We have 2 bonded pair and 2 lone pair. Okay, so we have the general formula of AB2E2 to work with. Okay, we'll come back to that in a second. And so here, this is what we just talked about. Okay, and we're done. Now, with that general formula, we go, and here's where the formula, whether I draw it like I draw that picture or how I drew it by hand, either one will work. But what do I know about the geometry? This is where now, because of the general formula AB2E2, I go to the shapes table and I look for AB2E2. And down in the bottom, right here, is the general formula of AB2E2. That gives me the geometry of water with that particular shape in the second column. Its name for that geometry is bent. It has a bent shape. And that bond angle between the two hydrogens is much less than 109.5. That's what the symbol less than. And that is less than 109.5 because those two lone pair, there's the two lone pair there, the EE right there and right there, okay? Because there's 4 electrons there. They're negative charge. They take up space. They repel each other. The result is the bond angle between the two hydrogens and the oxygens gets shrunk in. If that wasn't occurring, we would have a tetrahedral like the AB4 up there in the middle, up in the third entry from the top. The tetrahedral where everybody be equally all spread out around the central atom. But that's not the case because the lone pair occupy more space, okay? In fact, which takes us to another point. Anytime you have lone pairs on the central atom, okay, like in these 3 examples, anytime you end up with a lone pair in the central atom, that molecule, though it's covalent, will always be what we call polar. Okay, we have 2 types of covalent bonds and types of compounds, polar and nonpolar. You're familiar with these already. Oil and water. Water is very polar. Oil is nonpolar, okay? And once we figure out the polarity of the molecule, that's going to allow us to take one more step and figure out, if it's polar, it's going to be a lot more soluble in water than, say, oil, okay? And we're always remembering light dissolves light. Oil, material that has oil properties will dissolve more in oil solvents. Material that has more polar properties will dissolve more in polar solvents, like water. Water is very polar. All right, so that's our general formula. That's using the shapes table and so forth. Now let's try a couple of these here. A little more challenging. I'm going to see if I can pull up my let me get my paper here. See if I can use my pad. It's been acting up a little bit. Let me see if we can make it work. All right. First one, we have HCN, very poisonous gas, hydrogen cyanide. Okay. HCN. So what we have here is you're told the central atom. It's underscored. Okay. So carbon is a central atom, and bonded to carbon, we have a hydrogen and a nitrogen. In this case, it's hydrogens to the left, nitrogens to the right. It could be the other way around, makes no difference, okay? It could be NCH or HCN, HCN, either way. Okay, step number 1, we count up the valence electrons. And so for hydrogen, it's in group 1. And so for hydrogen, valence electrons equal 1. Okay? Carbon. How many valence electrons does carbon have? Anybody want to take a guess there? How many valence electrons does carbon have? Now, how can I find
4.
that? That's 4, right? I go find carbon. Carbon's in group 4, so I got 4 valence electrons. So I put up my 4. Nitrogen. How many valence electrons does nitrogen have? What we got, anybody? 5. Exactly. Wow, I'm just looking at my chat. I got like font size 50. It's just humongous. Isn't everybody else's font that big? Or just me? No? Okay. All right. So we got a total. We got 1 coming from hydrogen, 4 valence electrons coming from carbon, and 5 coming from nitrogen. Okay, that is a total number of valence electrons you got to work with. You can't add more, you can't subtract more. So you got to make this work. So we add that up, we got a total of T for total of 10 valence electrons, right? 5 plus 4 plus 1 gives us 10 valence electrons. I'm going to just call that VE, or divisible by 2, right? Or 5 pair. 5 pair. I just, like I said, I just like the work with pairs because you just can draw a line. You don't have to. You can put the dots, double dots in there. Just you can have a lot of dots down the road because you can end up with like 32 valence electrons. That's a lot of dots. Keep track of. So just drawing the line makes it much easier. And so we have 10 valence electrons or 5 pair to work with. All right. So what do? All right. So we know that carbon is the central atom. So I can very quickly type hydrogen. I'm going to use hyphen. My hyphen is my bond. And then another hyphen for nitrogen. Okay. So that took care of 2 pair, right? Because I got 1 pair bonded to the hydrogen, 1 pair bonded to the nitrogen. I have 5 pair to work with. So I got remainder 3 pair left to work with based on the 5. Now I can't put those, now I put those 3 pair anywhere you want, except you can't do it to hydrogen. Why? Because hydrogen is already full. So hydrogen has a duet rule. It has 2 pair around it already, is being shared with carbon. So that pair is shared with carbon and hydrogen, and it counts toward hydrogen and counts toward carbon. Okay, so with 3 pair, you can put them anywhere you want. I tend to want to stick them on the outside atoms and work my way in. So what I'm going to do is I'm just going to put them very carefully onto nitrogen, and if it allows me here. Okay, so I'm going to put 1 there. I'm going to put 1 there. And then I'm going to put 1 there. Okay. Now check my numbers there. Check my lines. I should still have 5 pair. Okay. One shared by the hydrogen, and 4 of them shared with, well, 4 of them, 3 of them around the carbon. Excuse me, 4 of them around the nitrogen, but 1 of them shared with the carbon. But I still have 5 pair to work with, or 10 valence electrons. Remember, each line represents 2 pair. Okay. And that's what, as you start writing these structures, you got to go back and check. Make sure you're still maintaining the number of valence electrons that you calculated to begin with, because it's very easily, you can very easily lose one of those lines and lose one of those electrons as you're making the formula. So periodically go back and check, do I still have 10 valence electrons for 5 pair? And yes, I do. Okay, now, once you do that, go back and check the octet and the duet. Hydrogen's duet is happy, so hydrogen's done. Nitrogen, its octet is happy, right? The way it's written, I got 8 electrons around nitrogen. 2 of them are being shared with carbon. So nitrogen's happy at this point. Carbon, however, is not. Carbon only has 4 electrons around it. 2 of them are being shared with nitrogen, and 2 of them are being shared with hydrogen. And so at this point, I need to take a pair of electrons on nitrogen and create a double bond. Okay. I create a double bond between the carbon and the nitrogen. In fact, I'm going to have to create a triple bond, because I can take one of these pairs and make a double bond between carbon and hydrogen. It still leaves me short for carbon, so I take another pair and make another bond. I end up with a triple bond. And the formula that I end up with is as follows. Okay. I still have 10 valence electrons. Okay. I still have 10 valence electrons around. One of them around the central atom carbon, one pair is being shared with the hydrogen. 3 pair are being shared with the nitrogen, and carbon and nitrogen has a lone pair on the nitrogen itself. You go back and check the duet. Nitrogen has 8 electrons around it. Carbon has 8 electrons around it. And hydrogen has 2 electrons around it. So the duet and the octet is fulfilled. Where I still have 10 valence electrons. I did not magically create any more electrons. I did not magically lose them. There's still 10 in there all the way around. So that is my formula. Okay. When you're at the point when one, like we just did here, carbon is shy 2 electrons, this is where you start creating single bonds and or triple bonds until such state that everybody's happy with respect to the octet. And that's what happened here, making the triple bond. Now we get the general formula. Okay. Now you don't have to get the general formula, but I hope you can see here that we have a linear structure. But if you don't, the general formula here would be AB2, right? AB2. And if you go look up the AB2 general formula, you'll find it to be linear, the very first one. It'd be a linear species. And 180-degree angle between the hydrogen and the nitrogen. Okay. All right, see how that works? Now, it gets a little more, not challenging, it's just more electrons to work. Let's take the next one. Let me clear my table. Okay, the next one, we have a carbon, central atom. It has bonded a hydrogen and 3 fluorides. 3 fluorides, okay? So, same scenario, similar. We take carbon, capital C, number of valence electrons like we did with the previous one, 4, right? Hydrogen. Hydrogen has 1 valence electron. What about fluorine? How many valence electrons does fluorine have? Okay, what group is fluorine at?
7.
7, exactly. Okay, and there's how many? 3 of them. Okay, and so we need 7 times 3. Okay, which is equal what? 21. And then we had 1, keep everything kind of even there. Yeah. Obviously equals 1. And then times 1, that's the number of atoms, equals 4. And so how many valence electrons do we have total to work with? Anybody want to take a guess? 21 plus 1,
26.
6. We got 26 valence electrons, or guess what? 13 pair. Okay. And so we have,
Sorry. Sorry.
what's that?
Why 13?
You broke up.
Sorry, why 13?
Why 15?
13.
No, you have 26 divided by 2.
Oh, okay.
Yeah. 26 divided by 2. Remember that number you get, valence electrons, will always be divisible by 2. So you have 13 pair, okay, to work with. And I say 13 pair because I just like to make lines. So here I'm going to try to do my what do you call it? 26 and 13 pair. Okay, based on the formula we're given, let me try to do whiteboard here. All right. We're given the carbon, so I can draw that. And since there's 4, I can very quickly draw the hydrogens, put 1 hydrogen, and then I can do the fluoride and another fluoride and the other fluoride. Okay, so that took care of 4 valence electrons. Did it not? It took 4 pair. It took care of this one, 1, 2, 3, 4. Now, how many pair do I have left now? Because I started with 13, I just used 4. What do I got left? Don't I have 9? Okay. And so I could very quickly put 1, 2, 3, 4, 5, 6, 7, 8, 9. So the yellow, I got 9. The blue, I'm going to put them in yellow too. 9, 10, 11, 12, 13. Isn't that what we calculated? Right. We calculated 13 pairs of valence electrons, or 26 valence electrons. Okay. And now the general formula that I have is I have A, okay, B, 4. That's a 4. Not a 9. It's a terrible 4. And it's a better 4. There's my general formula, AB4. That is the structure there. Okay. Carbon, the central atom. I got the yellows are all the pair. There's 13 of them in there. My general formula is AB4. Guess what?
The third one?
It's right here. AB4 is right here. AB4, that is my geometry. The name of that is tetrahedral, and that bond angle is 109.4. Okay. So that is the general formula for that example we just did. You see how we did that? I don't know, my whiteboard's still there. Yeah, it's still there. Okay, because I was given, originally was given, if you recall, I was given the hydrogen, the carbon, and then the fluoride. Oh. And originally, like I said, I was given hydrogen, then carbon, had an underline, and then I had 3 fluorides. That was the formula that was given in an example. And then from that, we added up the valence electrons and we ended up with 13 pair. And so I know that the carbon, the central atom, the 3 fluorides and the hydrogen, they're bonded to the central atom. So I very quickly put 3 fluorides and 1 hydrogen around the central atom of carbon, and I put a bond. I first put them in blue, but then I went and covered them in yellow color, which took care of 4 pair electrons. So 13 minus 4 left 9. I can't put any more on the hydrogen because the hydrogen's full. I can't put any more on carbon. Why? Because carbon already has 8 around it. So the only place they can go on would be on the fluorides. And so I went all the way around and put the remaining 9 in yellow around all the fluorides. In fact, you're going to find fluorides the fluoride, the chloride, the bromide, okay, and the iodide, like hydrogen, will only make one bond, and the rest will be lone pair. Okay. Oxygen, members in group 6, makes 2 bonds. So H2O, it had 2 bonds of hydrogen, right? All right. So let me clear this, and then we'll go back to that, and guess what that one looks like? There it is, just what we just did. Now, in my case, I made lines. You can put the double dots. That's up to you. Makes no difference whether the double dots or line to give you the lone pair. Count them. You can see we did the same thing. There are 13 pair here, 9 around the halogens, the fluoride, 10, 11, 12, 13, and 13 around the carbon or more. So we got 13 valence electrons. The octet is happy. The carbon has 4 bonds around it. That's octet. Remember, each line represents 2 electrons. So there are 8 electrons around the carbon. Its octet is happy. The fluoride has 8 electrons. All 3 fluorides have 8 electrons around it. One of them is shared with the carbon. The other 6 are on the fluoride itself. They're not being shared. Those are lone pair. Okay. All right. Now, let's do the next one, which I think would be a little more interesting here. Carbon dioxide. We're familiar with carbon dioxide. All right. If you drink carbonated drinks like I do, you got a lot of carbon dioxide. All right. So let's take carbon dioxide. We do the same scenario. We got carbon. Everybody agree there's 4 valence electrons, right? All right. 4. Oxygen. How many valence? There's 2 oxygens. How many valence electrons do we have total?
6.
6, right? 6, are you sure? How many do we have? Carbon dioxide. How many oxygens do we have? 2, right? CO2, right? Each one, you're correct. Each one brings 6. So what's our total number? Here, I'll keep up.
12?
12.
No, 12. Come on, guys. All right.
So,
Yeah. Let's go back and keep it consistent how we did before. Okay. We have 1 carbon. Okay. It's in group 4, so it brings 4 valence electrons. Oxygen. There are 2 oxygens, right? It's in group 6. So it's going to bring 12 valence electrons. And the carbon is bringing 4. Okay. Everybody see that? 1 carbon, group 4, 4 valence electrons. Oxygen, 2 oxygens, group 6, 12 valence electrons. That means we have a total of how many?
16.
You got it. You got total of 16 valence electrons, or how many pair?
8.
You got 8 pair, exactly. 8 pair. Now, you can keep it at 16 or use the 8, makes no difference. It's the same number at the end of the day, right? Okay, so we got carbon dioxide to work with. We got a total of 8 pair. All right. Now, we're gonna draw that. So let me bring up my white. Carbon is a central atom. Everybody see that, right? Because we highlighted, it's underscored. Carbon's a central atom. That means the oxygens are bonded to the central atom. And so let's start with that. We go to the whiteboard. And so I have carbon, and then I got one oxygen bonded, then I got my other oxygen bonded, okay? So we had a total of 8 electrons to work with, pairs. I just took care of 2 of them. What do we got left to work with? What's 8 minus 2?
6.
6, right? And so now, where are you going to put them? Here, you can put them anywhere you want. So I'm just going to go 1, 2, 3, 4, 5, 6. Okay, now count my lines. I still have 8, right? Total. I didn't add any more. I didn't subtract. Because we calculated to have 8 pairs of electrons for carbon dioxide. So there should be 8 total lines there. And there is. Okay. All right. If I look at here, I got 1, 2, 3, 4, 5, 6, 7, and 8. All right. Now look at the octet. All the oxygens are happy, if you will. There's 8. Okay. One of them is shared with the carbon, and the other 3 pair are on the oxygen. That's true for the one on the left, and that's true for the one on the right. But look at the carbon. The carbon only has 4 electrons around it. So what do we got to do? We got to make double bonds. Okay. We can take this one right here and make a double bond right there. We can take this one right here and make a double bond right there. The result is that we end up with, I'm going to make it a little bit different. I make carbon, double bonded oxygen, double bonded oxygen, and then I still got my lone pair. Okay. Do I still have 8? 1, 2, 3, 4, 5, 6, 7, 8. Yep, I still got 8 pairs. Do I have my octet? Yes. Around the oxygen on the left, I got 1, 2, 3, 4. Around the carbon, I got 1, 2, 3, 4. Around the oxygen, I got 1, 2, 3, 4. And I say 4 being paired, which means the octet is fulfilled. And so everybody's happy here. Again, my general formula is A, B, 2. Okay. AB2 is my general formula. I can go to the shapes table, and I will find that AB2 is linear in shape with 180 degrees from here to here. Okay. So you see how we did that one? And so we end up, and this is a unique property here we're going to learn about carbon dioxide because of its structure. So we end up with that, which is what we got. Okay, 8 pairs. Now, I'm going to do one more, and we're going to do nitrogen. And like we started, nitrogen, the last one is it got nitrogen, the central atom, and 3 hydrogens around it. Okay, so like we just did, we have hydrogen. Okay, there's 3 hydrogens times 1 valence electron gives us 3 valence electrons. Nitrogen, how many valence electrons does nitrogen have?
5.
5, in group 5, and there's only 1, right? So that equals 2, 5. So total, we have how many valence electrons? Was 5 to 8, exactly. 8 valence electrons, or how many pair?
4.
4 pair. Okay. And that's what we got to work with. We got 4 pair to work with. Okay. 3 of them are bonded, the hydrogens are bonded to nitrogen. So let's go back to the whiteboard. All right, let me clear this mess up here. And let's do this. So we have nitrogen. Oh, have nitrogen. Well, where's going on here? I lost my. Ah. So we have nitrogen. My thing's not okay. We got nitrogen bonded to hydrogen, one of them. Then we bond the other one to hydrogen, and then we bond the other one to hydrogen. Okay, so that took care of 3 pair. 1, 2, 3. Right? We have 4 pair to work with. We got to put it someplace. We can't put it in the hydrogen. Why? Because the hydrogen's happy. So the only place we can put it, guess what? Is on the nitrogen. Okay. And so hydrogen now is happy. We got the duet. We still got 4 pair of electrons to work with, or a total of 8 electrons. Remember, each line is, if I draw it like this, with 2 dots, it's the same thing as that what I draw it by the lines. Okay, remember that. And so I have this general formula here. And now I got my general formula. Let me make that a different color so we know. Okay, so we have A, B, 3, E. Okay, A is the central atom. B is what's bonded to the central atom. In this case, 3 hydrogens. That's a 3. And then we got an E. Why? Because we got a lone pair on the central atom. And taking that information, we go to the shapes table, ABE3, and guess what we have right here? That is AB3E. The geometry is given here. We got a lone pair in the central atom, like we just draw. It's trigonal pyramid, and that bond angle is less than 109.5. And one additional bit of information, remember, when you have a lone pair on the central atom, automatically polar compound. Okay, polar compound. Hey, all right, remember that. On the central atom, automatically polar compound, because we're gonna use this information down the road when we talk. Is it polar or non-polar? Okay, and it meaning polar, meaning that it's going to be water-like as far as solubility. Going back to the formula, we end up with that. Okay. That, by the way, is the formula for ammonia. So next time you're cleaning a window, you get that ammonia smell. That's what you're smelling, NH3. Carbon dioxide, and that's what plants like, and that's what we exhale. That is the structure for carbon dioxide. Trichloromethane, that's a CHF3. That's what we call a halogen. Remember halogenated hydrocarbon, which is not a good thing to get out there. Not to get a good thing to get out there in the atmosphere, because it reacts with UV light and then forms compounds that react with the ozone. You may be familiar with ozone. There's 2 types of ozone. 2 places where you find ozone? Here, and you have the ozone alert here in our air is bad for your breathing, but you have another layer of ozone way up in the atmosphere, which protects us from the UV light. You're familiar now with ultraviolet. We talked about the electromagnetic radiation. And if these hydrocarbons that were used a lot of propellants have gone up to the atmosphere and destroyed our ozone layer up there. It's a very small layer, and it's caused more UV light to come down to Earth, which causes a lot more problems, skin cancers, attacks plants, and so forth. So Anyway, what I'm going to do here, I'm going to stop it here on this particular slide. This chapter is going to take a little extra time, more so than normal. And what slide are we on? We're on 19. We didn't get too far, huh? That's okay. Okay. Now the next, this is the next slide here is what we just talked about. Okay. The next thing is we're going to talk about Lewis dot structures for polyatomic ions. Now, what is polyatomic ions? I direct you to the periodic table on the bottom left corner. Most common polyatomic ions. Okay. Same process, except these guys have a charge to them already to begin with. We're going to be able, you have to determine, do we subtract or we add? All right, so let us stop here. And we'll start again. And once we get past this slide, it will go pretty quick.